All right, so I'm going to start this second video lecture set, just going through some of the homework problems that I think might cause some problems. Um, and, uh, and yeah, so we'll start with number 8 on this worksheet right here. And it says, consider a wave generator that produces 10 pulses per second. When they tell us that, 10 pulses per 1 second, that's the same as saying frequency, right? So they're saying 10 cycles per 1 second, which is equal to a frequency of 10 hertz. But I think you just got to recognize that that is the frequency. Then they say the speed of the wave is equal to 300 centimeters per second. And we should remember from class that 100 centimeters is equal to a meter. So we can do the conversion really quick. It's obviously going to be 3. All right, so we have a velocity of 3 meters per second. We have a frequency of 10 hertz. And so the question they're going to ask us is, what is the wavelength, right? And we should remember from our notes that our formula, our relationship between velocity, frequency, and wavelength is V equals frequency times wavelength. So we can go ahead and plug our 3 in for the velocity, our frequency of 10 hertz, and then our wavelength is what we're solving for. Divide both sides by 10. And this is going to give us just meters left over. The seconds is going to cancel the per seconds on bottom, or the hertz. So that's kind of tricky to look at. It kind of ends up looking like this. You got meters per second on top, and then you got 1/seconds, which are hertz, on bottom. So the seconds on the bottom goes to the top, and the seconds here goes to the bottom. So it ends up looking like this: meters per second, and then this seconds on the bottom, a fraction inside of a fraction, floats up to the top. So it ends up just being meters. Anyways, 3 divided by 10 is 0.3. Units are meters. And there's our wavelength. This is for number 8A. And then 8B says, what happens to the wavelength if the frequency of pulses is increased? And what happens to the wavelength if the frequency is increased? If F is increased, we said that the speed is going to stay the same, right? That the speed of the waves is 300 centimeters per second, or 3 meters per second. So if we increase the frequency, we will decrease the wavelength, because this is constant. So what happens to the wavelength for 8B? We would say decrease. All right. Good. Let's go ahead and look at number 9. Yeah, I'll just work off here. Number 9 says a wave on Beaver Dam Lake passes by 2 docks that are 40 meters apart. So let's start by drawing. We'll draw a dock here. And we'll draw a dock here. It's kind of like we're looking from above at the docks, right? And it says that they're 40 meters apart. Okay, so far so good. Then it says if there's a crest at each dock and another 3 crests between the docks, determine the wavelength. So now it comes down to drawing this accurately, right? So we want to put a crest right here and then 3 crests in between. 2, 3. All right, so it's going to look something like that. So what I have there is a crest here and a crest here at each dock, right? And then 3 crests in between. So how do we make sense of this, right? Well, let's go from crest to crest because we know that crest to crest is a wavelength. And I just want to point out equilibrium is right there. Just so you can kind of make sense of that because you don't see an equilibrium line, but I always like to draw this, and that actually will help, I think, say in a problem like these right here, if you draw your equilibrium in like it was right here. All right, anyways, so we know this is one wavelength, but we don't know what this is. But I bet if we divide this up in wavelengths, maybe we can get some understanding of it. So what I'm saying is, let's go crest to crest again. There's another wavelength. Now you might say, well, shouldn't this be the same length as this? Yeah, my drawing's pretty terrible. All right, let's go crest to crest again. All right, and crest to crest again. And you can see where this is going, that this, we are able to fit 4 wavelengths in 40 meters. So what's 40 divided by 4? We should be able to say, well, then a wavelength is equal to 10 meters. All right. Part B, that was 9A. If 10 waves pass one dock every 16 seconds, determine the period and frequency of the wave. All right, so this is 9A. In 9B, 10 waves pass one dock every 16 seconds. So they're telling us something right there, right? They're telling us the frequency. Frequency equals the number of cycles per second. So we're going to say 10 waves every 16 seconds. So this isn't in per 1 second, right? And so let's fix that, right? So if we just divide this, 10 divided by 16, we can go ahead and get that answer. So I'm going to snag my calculator. I guess it's the same as 5 over 8. But 10 divided by 16 is equal to 0.625. So what we're saying there then is the frequency is equal to 0.625 waves per second. So that's how many waves pass the dock, a little over half of a wave every 1 second. Now we can consider that a cycle and just call this, then the frequency is equal to 0.625 hertz, right? Or cycles per second. All right. And we can get the period the same way, right? Using these same numbers. I could just say F equals 1 over this, or I'm sorry, T equals 1 over this, but I'll show you the first way. I'll show you maybe both ways. All right, so there's my frequency. The period is equal to the number of seconds per cycle. All right, so now I can just go ahead and take 16 divided by 10 and get that the period is equal to 1.6 seconds per cycle. And since it's 1.6 seconds per wave, right? So it takes, per one wave, it takes 1.6 seconds for one wave to pass a dock, is what we're saying. Which makes sense because in 1 second only 0.625 waves passed. So how long does it take for a whole wave to pass? Well, 1.6 seconds. All right, so but usually we ignore cycles. They're kind of a shadow unit. They're not really there. So a lot of times we'll just write the period as 1.6 seconds. Now you very easily could have got that same answer by just saying, well, T equals 1 over F. And then therefore T is equal to 1 over 0.625 hertz. And then type that in your calculator. 1 divided by 0.625 is equal to 1.6. All right, so 2 ways to solve the period there. And that's how you get the frequency for 9b. C, what is the speed of the wave? So for 9c, we can just go ahead and say V equals frequency times wavelength. V is equal to 0.625 hertz times, what was our wavelength? 10 meters. All right. So 10 times this is going to equal a velocity of 6.25 meters per second. All right, pretty good. Let's go ahead and go to problem 10. In number 10, it says Sally Sue, an enthusiastic physics student, enjoyed the opportunity to collect data from standing waves in a spring. Standing wave is just a wave that doesn't really go anywhere, it just moves up and down, kind of like a jump rope. And all right, from standing waves in the spring, she and her partner held the ends of their spring 4 meters apart. Okay, so there's a node in each location. They hold the spring. It's at equilibrium right there. There were 5 nodes though in the standing wave produced. Okay, well we have to count the 2 where they're holding it, but there's going to be 3 more between them. All right. Sally moved her hand from the rest position back and forth along the floor 20 times in 4 seconds. Well, 20 cycles in 4 seconds. So they're giving us a frequency there. Sketch because a cycle is to go there and back. All right. Sketch the situation and determine the following. Okay, so the first one says, well, let's start with a sketch, right? That's always the best way to start. So we're saying there's a node, then there's 3 more nodes, 1, 2, 3, and then another node. Because this is where they're holding, right here at the ends is where they're holding the slinky, right? Or the spring. And then we can go ahead and draw the standing wave that's produced. So I'm going to start with a sinusoidal wave, and then I'll kind of show you how a standing wave looks a little different. Okay, so standing wave is going to do this at one time. Whoops, at one time, and then let me see if I can. This pen's dying a little bit on me. Okay, so, and then at a later time, it's going to look like this. Right? So this is what I mean by standing. The nodes don't change, right? Instead, this spring just goes, back and forth. And is it only at these 2 locations? No. It can be in between, right? It could also be at this location right here. Right? Oh, I just covered up all my nodes. Dang it. It could also be at this location right here. It could also be at this location right here. So this standing wave has these antinodes. How many? 1, 2, 3, 4. 4 antinodes. We call that 4 modes. The 4th mode here. And it's pretty neat. But anyways, where were those? I should probably draw in those nodes again. Node isn't the same as mode, but anyways, I don't want to confuse you there with that. So here are my nodes with an N, N-O-D-E, 1, 2, 3, 4, and 5. So there's a node at each of their hands, and then the standing wave that just goes, back and forth like that. And so now we can start to think about, well, what's really happening here, right? It says that she and her partner are 4 meters apart. Okay, so this distance right here is 4 meters. Well, does that help us find the wavelength? Kind of, sort of, right? I think it depends on, that's part A. That depends on how we think about wavelength, right? I don't like crest to crest here because I'm having a hard time visualizing that. I think I like node, skip a node, next node, right? So this distance right there is a wavelength. And if we go node, skip a node, next node, this is also a wavelength. So therefore, how many wavelengths long, or how many meters is a wavelength? Well, obviously 2, right? And there's our answer to part A. Part B, 10B, what is the frequency of the wave produced? Well, they told us some numbers, right? They told us that she moves her hand back and forth from the rest position along the floor 20 times in 4 seconds. So we can say 20 cycles. I'll go ahead and say F, right? Frequency is equal to 20 cycles per 4 seconds. You do the math there, it's pretty simple. 20 divided by 4 is 5 cycles per second, or 5 hertz. Okay, so there's our frequency. And then finally, what is the speed of the wave? Well, the speed of the wave, so there's part B. And then part C, you should say, we'll use that fundamental relationship, right? V equals frequency times wavelength. V is equal to 5 hertz times, what's our wavelength? 2 meters. So we're saying our velocity is equal to 10 meters per second. We always want to make sure we're using meters for our wavelength and meters per second for our velocity. All right, good. I guess we can look at number 11. It's kind of related. It says, what frequency and period would be required for Sally and her cheerful, pleasant, hard-working partner to produce a standing wave with 3 nodes? Explain your reasoning by identifying your steps. Okay, that's interesting. I wanted to make a connection there with the last problem, but let's solve it first and then go from there. So for 11, if we have 3 nodes, right? So we're still saying they're 4 meters apart, right? So it's going to look like this, right? So we'll have a standing wave that looks like this. The next second it might be here. So now there's 2 antinodes and 3 nodes, right? Node, 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 antinode, antinode. This is a standing wave. It's not going anywhere. These are created by 2 waves that are moving towards each other, passing through, interfering constructively right here, destructively right here, hitting the boundaries and reflecting back. So it's 2 moving waves with the same wavelength and the same frequency creating this. Coming back to this problem, this is still 4 meters. What is the wavelength? Well, the wavelength is node, skip a node, next node. So this would be the wavelength, 4 meters, right? what else can we say? They wanted to know what would the period and the frequency be. Well, we know the velocity, right? The velocity didn't change because it's the same spring. And so therefore the velocity is equal to what we solved for before, which is that 10 meters per second, right? Okay, so we can say then that v is equal to 10, and we can go ahead and solve for the frequency, right? F equals, v equals frequency times wavelength, F equals v over wavelength. We can then say F is equal to 10 meters per second divided by 4 meters. And that's the same as 5 over 2, which is 2.5. Now, can I make some connection there between these two diagrams and the frequency? I think I can. We can see that when our antinode number went from 4 to 2, it halved, that the frequency is, I'm counting these as modes, M-O-D-E, not nodes. These are nodes, these dots in the middle where there's destructive interference. I'm talking about where there's constructive interference, and calling that a mode. So this would be the fourth mode. The frequency is 5 hertz. The second mode has a frequency of 2.5 hertz. And for the first mode, which would look like this, I'm not doing the calculation right now, but this is kind of neat for you to see. This one totally looks like a jump rope, right? It's still 4 meters this distance. What's the wavelength now? Ooh. Well, in this case, you have to pretend that the string is longer, the spring is longer, right? And now it should be obvious. Well, the wavelength would be this distance, which is what? Well, 4 meters plus 4 meters, right? Or you could say that 4 meters is equal to half of the wavelength, right? Because 8 meters is equal to the wavelength. Just do the math there. Divide both sides by a half, multiply both sides by 2. Wavelength equals 8 meters. So the frequency of this wave, right, when the wavelength, did it double? Yeah, it doubled. When it doubled, the frequency is going to halve, so F is going to equal 1.25 hertz. And so what we're seeing is that this mode number, right, this is the first mode right here, right? I count 1, right, 1 mode. It has multiples of its frequency. This is the fundamental frequency of the first mode. In the second mode, we have 2 modes, 1, 2, right? So this is the second mode. And in this one, the frequency is 2 times the fundamental. Well, the fundamental was 1.25, so 2 times that is 2.5. And then in the fourth mode, this is standing waves for you, 1, 2, 3, 4. Well, I would say the frequency is 4 times 1.25. Is that right? Is 4 times 1.25 equal to 5? Yeah, of course it is. 4 times 1 and then 4 times 0.25. So 5. And this shows up when you think about this idea of standing waves. When you think about musical instruments and whatnot, they kind of operate based on standing waves that they create inside of their open, closed or open tubes. So maybe if I get time, I'll come back and talk about this, but I'm not sure how much I'm going to go into it. But that's kind of like a little bit of it right there. All right. So did I answer the question? It said what frequency and period. I think I got the frequency. If I go back to that, it was right here. The frequency is 2.5 hertz. I didn't get the period. So the period would be T equals 1 over the frequency. So T is equal to 1 over 2.5 hertz. What is that equal to? I don't know. I need my calculator. 1 divided by 2.5 is equal to 0.4. So this is equal to 0.4 seconds. Or you could say seconds per cycle if you wanted. but that's the period. So the period is 0.4 seconds, and the frequency is 2.5 hertz. This is for number 11. Okay, go ahead and pause it there. Okay, so for the next part of the assignment, it's going to be about superposition or interference. And when we look at this, what I like to do here is kind of label these waves. I have two waves that are approaching each other. Maybe I call this wave A and this wave, I don't know, B. And it's a model, right? It's not supposed to be perfect. And that's something to keep in mind here. I'm going to give each of these waves a little bit of color. Maybe the A wave, I'll give it some blue color. I'm not sure how well that's coming through. And then the other wave, I'm going to give it some red color. The B wave. Okay. And what you do with these is first you look at the speed of the waves. In this example, which is from the homework, the waves are moving 2 blocks per second towards each other, right? And these little arrows say they're moving towards each other. So after a second goes by, we're going to draw what happens. Now, usually they want to know about, I'm just going to go ahead and draw an equilibrium line, which is this black line right here. They want to know about, I'll call this t equals 0 seconds, this t equals 1 second. They want to know what happens when they meet, right? But I'm going to draw all the times in between. Obviously, I might run out of room. I got a separate sheet of graph paper here just in case, and I'll make sure there's one on Schoology. But you don't need graph paper. You can probably do this on lined paper, but it's a little tougher, right? It's easier to visualize with graph paper. So this blue wave, its front is right here. And in a second, if it goes 2 blocks, it's going to go to right here, right? This point right here. So what I'm going to do is come down here, right, which is 2 blocks ahead, and make the front of this A wave or this blue wave, right? That this is where A is now. Okay, and that's 1 second later. I'm going to do the same thing with the B wave or the red wave. The front of it's right here. In a second, it's going to go 2 blocks forward to here. So that's where I'm going to make the front of the B wave. And so what you can see, now keeping in mind, these waves don't have color. They don't have letters really. They are just like, you can think of this as just 2 chunks of a string moving towards each other. And so ultimately, you would just see a giant string that looked like, that had this black shape, right? I don't know if you can see it. I lost my, let me see if I can get my pen here. So it would be a string that looked like this, right? And that's ultimately what you would see, right? And it's just the string with these 2 upwards displacements moving towards each other. And so that's something to keep in mind here. So I'm going to go one more, I'll draw one more equilibrium down here. Now, I know these are going to stack right here, so they're going to add together. I'm going to give myself a little more room this time just to make sure I can fit all of that displacement in this, on this graph. So I'm just going to draw the equilibrium line down there. Label t equals 2 seconds, right? So at time 2, the front of the A wave is now forward 2 blocks, right? Because it's a second later. So the front of the A wave is right here. The front of the B wave is going to be right here. So I'm going to get my red marker. It's going to move over 1, 2, and be right here. Okay, so you might say, well, how do you draw it? How do you color it? Which block is on top, blue or red? It doesn't matter, right? That's not the point of it. So I'm just going to go ahead and pick one. I'm going to put A on bottom, all right? I'll put B on top. But the point of this is the A and B and the red and blue is just to help me make sense of it. Because really what I have here is a 4 high, right? That this wave has a larger displacement when these two meet, right? So the string would look like this right there. And this bottom of this wouldn't be here, right? It would just be that. And then a second later, because we do have space, if you run out of space and you can't draw the after of these, that's fine. But I'm going to do it because I have space. At 3 seconds, I know start with an equilibrium line, that the blue wave will now move 2 forward, 2 blocks a second, right, to right here. So that's going to be right there, and that's where A will be. And B will move 2 forward from here to right there, so I kind of just follow it down. And B will now be here, continuing to move this way, and A will be here, continuing to move this way. Both are unaffected and they pass through. All right, so this would be superposition happening right here at time 2 seconds, and we can see that it's constructive interference, right? And that would be a question that they might ask, right? They might say, well, at what time would both waves interfere? And you would say 2 seconds, right? They might say at time 2 seconds, draw the wave, and you would draw a larger displacement here. So I'm not going to do all of these examples here because this will be part of your homework, but I'm just showing you this. Now, they don't always have to hit and overlap completely. I think question 6, they just shift past one another. So let's go ahead and try this. So 6 has a wave that is downward and is a 4 low, and a B wave which is upward and is a 2 high. So I'm just going to go ahead and label those. Once again, the A and the B are just to help me make sense of it and just so I can talk to you about it clearly. I could just call it blue and red. I really didn't need the A and the B once I have the colors. Okay, so I'm going to go ahead and make, this is time t equals 0. What's going on at t equals 1? T equals 1 isn't going to be very exciting, so I'm going to move down just a little bit, maybe right there. Could I skip time equals 1 and go right to t equals 2? I could, but I want to make this as clear as possible. So once again, they're moving 2 blocks a second, so A is going to be right here. Follow this down, and so right here, and it's going to still be a 4 low. And I always refer to where the front of it's going to be, right? Because obviously the back of it's going to be back here, and it's going to, back of it moves forward too, the front of it moves forward too, and so the A wave is going to be right there, the blue wave, and the red wave is going to move forward too from right here. The front of it will now be right there, and so I can go ahead and draw that as a 2 high right there. And just for some continuity, I can label these A and B, and so you can kind of see. A second later, and here's a case where they're just going to shift past each other, right? So at time equals 2 seconds, let's see if I can draw this. The problem is this is just on too small of a sheet, right? I just don't have enough room to keep going here, so that's why I have the extra graph paper. So I might have to break that out here. All right, so at time equals 2 seconds, the blue wave is going to shift forward 2 to right there, so it's going to be right here, and it's still going to be a 4 low. And the red wave is going to shift forward to right here. This front, the two fronts are going to meet right there. It's going to look like that, and this is where B will be, and this is where A will be. So in the next second, they're going to shift onto the other side. So B will be on this side and A will be on this side, and these will never interfere, right? They just shift past each other. It's just the way it worked out, right? But if you were watching the string, right, you would see something like this. So you'd have like kind of like a negative sine wave there that's kind of looking like, and I don't know, but it would look like that, right? So in a second later at t equals 3 seconds, even though I don't have graph paper, I could probably still draw it down here. Let me see if I have enough skills to do that. T equals 3 seconds would look like this. See, the front of the blue wave would move to there, the front of the red wave would move to there. So I'm thinking something like this, right? Yeah. All right, because A is now shifted to here, and B is now shifted to here. So you can see where this is what the string would look like, and the red and the blue are just there to help us visualize, right? Whoops, B, G's, A. All right, that is a B. Okay. Good. Kind of looks like it. Okay. So yeah, that's it. Pretty straightforward. And really this is what we're looking for here, but it's nice being able to draw every second of this, and that way you can show the most understanding. And then obviously a second later at 4 seconds, B would shift even further, A would shift even further, and so on. Okay, so never a point where they completely overlap there, just because of that's just the way it went. It's just where they were located, and yeah, so sometimes it doesn't work out that way. All right. Had they have overlapped completely, what would have happened, right? If they had started at different locations and they could have overlapped completely, then all of the up part of B would have been canceled by a similar part of A, and we would have had a 2 low right here. So it would have went down, but just two down, right? And all right, I got cut off there. But anyways, I'm going to move on to one more example of interference or superposition. And these questions that we just did right here, you can finish the rest of these for homework. And hopefully this next example will help. So there will be 3 worksheets for the homework. The front of this worksheet, really you just got to use the fundamental relationship of a wave, V equals frequency times wavelength, and then rearrange this if necessary, right? What would that mean? Well, frequency equals V over wavelength, or wavelength equals V over frequency. So you can solve for velocity, frequency, or wavelength using these right here. All right, so that's pretty straightforward. The back here, we're going to skip the first 2 on the back because these deal with the type of problem involving energy and amplitude that I didn't get to. So we're not going to worry about that. This one right here, I just made a video over it and it got deleted somehow. So I'm going to make another video right now just talking about how I did the problem and going through it. So what we have here is a more complicated version of the interference ones we just did. And in this one, we got like a positive and a negative together, right? This blue wave here meeting this red wave, all right? And this red wave, once again, is more complicated than ones we did before too. So they're moving this time at 1 block at a time. So that's 1 block a second. This blue wave is moving to the right, and this red wave is moving to the left. So are they going to meet? Are they going to definitely? Are they going to interfere? Sure. At what time? That's a good question. So we're going to kind of find that out. Well, let's see what happens a second later, right? A second later, not much has changed. You might say, why do I have 3, 2, 1? Why do I color these? Just so I can talk about them and it's easier for me to see what's going on. There's no color or numbers really going on here, right? So when this this blue wave shifts, it's just going to shift over to the right one. So 3 moves over to the right one, 2 moves over to the right one, 1 moves over to the right one. A moves over to the left one, B moves over to the left one, C moves over to the left one. And so that's what you see right here. All right, a second later, we expect the same thing to happen, but now A is going to meet 1, right? And you can, if you're writing this down right now, you can print this off. This is just kind of an example problem. It's on, this is going to be on the assignment I post on Schoology. So maybe you can hold off on writing it down if you just want to pay attention. But if you want to write it down at the same time, I understand completely. All right, so a second later, A and 1 are both going to occupy this middle square right here, 1A, right? And what's going to happen, right? 3, 2 is going to shift over, BC is going to shift over, but none of them are going to meet, right? But 1 and A will meet right in this middle square. Well, what happens when a 1 high meets a 1 low? Positive 1 meets a negative 1, we cancel and have 0. So the waves are going to cancel right there in that middle square. And that's what I tried to draw there, right? With a 1A, I dropped down like 4 squares just to have enough room to draw my equilibrium line, right? Time equals 2 seconds, labeled that. But destructive interference where the fronts of the waves meet. The rest of the waves don't notice it at all, and that's fine. All right, a second later, this is the most confusing one, because what's going to happen here is that 1 is going to continue to shift this way. So 1's going to want to be here, 2's going to want to be here, and 3's going to want to be here. But if you remember that, so we're going to occupy, 1, 2, 3 is going to occupy these 3 squares. ABC wants to shift, A wants to go here, B wants to go here, C wants to go here, right? Because ABC is moving that way. And if that's the case, then what I'm trying to say is A is the front of ABC is gonna occupy the same square as the back of 1, 2, 3. So A and 3 are gonna wanna be right here. 2 and B are gonna wanna be right here. And 1 and C are gonna wanna be right here. So this is gonna be complete interference. What kind? Well, it depends on what happens when they meet. So let's look at the what happens. This is actually the answer right here, right? 3 and A meet in this square right here because 3 shifted over like this and A shifted over like this. When 3 and A meet, 3 is really a 2 high, A is a 1 high. Plus 2 and plus 1 gives you a plus 3. All right, that makes sense. 2 moves over to here, B shifts over to here. So 2 and B meet right here, but 2 is really a 1 high and B is really a 1 low. Positive 1 meets a negative 1, that's 0. All right, what about when 1 and C meet, right? Because 1 wants to go here, C wants to go here. Well, I don't know what 1 is because it disappeared, right? And the same with A. So I had to remember that 1 is really a 1 low, right? A is really a 1 high. And that's why when A met 3, right, a 2 high and a 1 high, I have a 3 high, right? This is a temporary change when they look like this. So just like this is a temporary change right here, right? The waves are going to stay like this, assuming no energy is dissipated over time just from things like friction or whatever, air resistance. All right, so we were at 1 and C, right? What happens when 1 and C meet? Well, 1 is a 1 low, C is a 1 high. Well, they would cancel. So we see this. So at time 3 seconds, we see complete interference, constructive right here at this point, destructive here, destructive here. Okay. Okay, in the next second then, 3 wants to shift away, right? Because it's, wait, 3's going this way, I'm sorry. A wants to shift over here. B wants to shift here, right? C wants to shift here in the middle. 1, 2, 3, 1 wants to go here, 2 wants to go here, and 3 wants to go here. So what I'm trying to say is because the waves want to continue past each other, they're only going to overlap at the very back of their wave. So 3 is going to end up overlapping with C, but A and B will already be on that side, and 1 and 2 will already be on that side. So what it's going to look like is something like this. And you can see where I drew, before we look at the shape of it, let's just look at the numbers and the letters. A shifted over to here. B shifted over to here. C shifted to here, right? Because ABC was moving left. 1, 2, 3, 1 shifted over to the right, 2 shifted over to the right, and 3 shifted over to the right there. And so the backs of both waves have some kind of constructive or destructive interference, and A and B is doing its original thing, and 1 and 2 is doing its original thing. So that means what happens, right? Well, A and B, since they get to do their original thing, A is a 1 high, B is a 1 low. All right, A is a 1 high, B is a 1 low. Okay. 1 and 2, same thing, right? 1 is a 1 low, 2 is a 1 high, all right, doing its own thing. All right, but what happens when 3 meets C? 3 is a 2 high, C is a 1 high. Positive 2 plus positive 1 is positive 3, and that's what we see right there. So just a little bit of interference going on. All right, one more second, right, to see, to finish the problem. So 1, 2, 3 wants to continue past, keep going that way. ABC wants to continue past, keep going that way. And that is what that shows. So that shows that you understand exactly how that's happening, right? 1 wants to move one more to the right, 2 wants to move one more to the right, 3 wants to move one more to the right, and it is back to its normal wave that it started with right here at the top, right? Check that out. Those are the same. Continuing to move right. Same thing is true of the red wave, continuing to move left, back, looking like normal at time 5 seconds. So that would be a good question on a test. Draw 5 seconds, right? And you would have to draw the two waves on opposite sides of each other, or from where they started, and moving away from each other. Okay, hopefully that makes more sense now. If it doesn't, well, first day, right? Our first time talking about this, so what do you expect, right? You can't expect to understand everything perfectly the first time through on the first day, because that's ridiculous. That's not the way learning works. Okay, so good. All right, so your homework then is to finish the front here, finish the interference practices, and there's more on the back. Good times. And then finish this worksheet, which we started right here too. And this has a couple problems. Looks like 2 problems on the back, and that's about it. So that's it. Yeah. All right. Have a good rest of your week, and let me know if you have questions. And take care.